In this video, we're going to look at the cross product and applications of the cross product. Suppose we have two vectors, u and v, that are not orthogonal, nor, that should be not for, nor parallel. And we want to find a third vector that will be orthogonal to both of those. What that means is that our u with the dot product of w and v with the dot product of w must both equal 0. So we end up with this. Multiplying component by component, the correct components adding up, this has to hold true. Now, if we treat these as a linear system and we start trying to do a substitution or elimination, we'll get something that looks like this. Then if we select what we are going to define W1 to be and W2, so each component, and then of course W3, we're going to end up with this lovely thing, which gives us how we're going to define the cross product. And you're going to say, wow, that's like the best formula I've ever seen in my entire life. How am I ever going to remember that? What is this coming from? Well, it's coming from this up here. How are we going to remember it? Well, let's walk back and think about how we found the determinant of a matrix. Now, this is the formal definition of the determinant of a matrix. And this explains why, by the way, we have to do the plus and minus shenanigans when we start to do the cofactor expansion. So you'll see that with this, it ends up having to have a negative and positive in all the correct places. And so going through the determinant of a 3 by 3, we can go out with a cofactor expansion. One of the ways that we can do this is using the definition. So it would be 3 times the determinant of, and I knock out this row, this column, it'd be the determinant of this smaller matrix. And then it's always minus, it's always plus minus. So it's plus if I expand out this row and column. It's minus if I expand out first row, second column, and it's a plus if I expand out first row, third column, and then etc. So then it's going to be minus, okay? So minus 2, and then the determinant of knocking out this row, this column, my smaller matrix is 4, 6, negative 3, and 2. And then, of course, my last one, remember, it's going to go plus, and so it's a plus, a minus, and a plus, and that's how come that's a minus, just as a reminder. And then it's going to be plus, even though it's a negative 1, so it's a negative 1, and we would knock out this row, this column, and then it's the determinant of the smaller matrix, which is 4, 1, negative 3, negative 1. Now we have this determinant of a smaller 2 by 2. So I have a determinant of A, B, C, and D. Then it will be A multiplied by D minus C multiplied by B. So that is the determinant of a 2 by 2 matrix. So if I take my matrix 3, or take my number 3 and multiply it by this smaller matrix, then what I'm going to get is I'm going to get 3 multiplied by, I have 2 times 1, which is 2, minus a minus 6, minus 2, and then inside I'm going to have 8 minus a minus 18, and then I'm going to have minus 1, and then on the inside I'll have negative 4, and then minus a minus 3. I add all of this up, and I end up with negative 27. I'm going to do the similar kind of algorithm when I'm trying to find my cross product, and I'll show you how that's going to work. Let's do the determinant of this matrix, but we're going to do it slightly easier, and then we're going to see how we're going to apply it to the cross product. So with this determinant, the other way that you can write this determinant is you repeat the first column, and you repeat the second column, and then multiplying down the diagonal, because you have to have 3 of them, will always be pluses. So it'll be negative 3 multiplied by 5, multiplied by negative 5, plus, multiplying down this one, it's going to be 1 multiplied by negative 8, and then multiplied by 4. And then down my last diagonal here is plus 2, 5, and 2. Multiplying up, these will all be subtractions, so it will be minus 4 multiplied by 5 multiplied by 2. Multiplying up this way, it'll be minus 2 multiplied by negative 8 multiplied by negative 3. And then this last one, minus negative 5 multiplied by 5 multiplied by 1. And then I add these two sets of numbers. So I'm going to get a set of numbers up here. I'm going to get a set of numbers down here. And then I'm going to add these two numbers together. And in this case, my determinant is equal to 0. We're going to talk about what happens when we get a determinant of 0. Right now, we're just going to say it's equal to 0. So we're going to use that information to find the cross product. So the way I'm going to write this is, I know that this is the I component, the J component, and the K component. So I'm going to make my matrix with I in the first row, then J, then K. Then I have 3, 2, negative 1, 1, 1, and 0. So I'm going to find the determinant of this. This will give me an IJK. So I have I multiplied by the determinant of my smaller 2, negative 1, 1, 0, minus J multiplied by the determinant of my smaller matrix, which is 3, negative 1, 1, and 0. And then my last one, let me just erase this out of the way. My last one is plus K, and then the determinant of that smaller submatrix, 3, 2, 1, and 1. What will end up happening is I will end up with an I. When I multiply that out, I will get an I, and then I'll get minus J, and then I will get plus K. So this vector ends up becoming 1, negative 1, and 1. This vector right here is orthogonal, so it is normal to both simultaneously my vector u, and my vector v. So I have found a vector that is orthogonal, in other words, normal, to both of those two vectors. So if I did the dot product of u, and let's call this w, if I did the dot product of u and w, I'll get 0. If I did the dot product of v and w, I will get 0. That w is orthogonal or normal to each one of those other two vectors. Let's take a look at the second example. Again, I have my I, J, and K. My first vector does not have an I, so I put a 0 as a placeholder, then 2, then 3. My other vector does not have a J, so it would be 3, 0, and 1. And the determinant of this is going to be the determinant of, actually, let me do it this way. It'll be I, I don't know what that was all about. It will be I times the determinant of the smaller 2, 3, 0, 1 minus J times the smaller 0, 3, 3, 1, and then plus K, and that would be 0, 2, 3, and 0. And when I get done with this, I end up with a vector that is 2I plus 9K minus 6J. So in other words, 2, 9, and negative 6. So that is the cross product. Notice that when I do the cross product of two vectors, the answer is a vector. So cross products produce another vector. It produces an orthogonal or a normal vector to my original vectors. My cross product follows the right-hand rule, and this is going to be important when we're talking about torque. Notice if I have this vector u and this vector v, if I were to cup u and v and rotate in a regular positive rotation, remember positive is a counterclockwise, then the resulting vector will be straight up. Now, if I were to rotate in this direction, my vector would go down. So what will happen is u cross v is not going to be the same thing as v cross u. It'll be similar, and this will be important on the homework. U crossed v is going to be negative v crossed u. So if you want to find two normal vectors, one in one direction and one in the other, is you do the negative of it and you'll get the other one that you need. So these are the properties. U crossed v is the negative v crossed u. I have u crossed with, and so I can do the addition of those two vectors first and then do the cross product, or I can distribute it. I can do the scalar onto one vector or the other vector and then do the cross product, or I can do the cross product first and then multiply by the scalar. If I have u crossed v, this is the only time that it is when this is 0, is when 0 cross u is the same thing and it happens to be 0. The cross product on itself is equal to 0. And then we have something called the scalar triple product, which means we're going to get this cross product, and then we're going to multiply, which is going to be a vector. Then we're going to do the dot product on that on my other vector, which will, of course, produce a scalar. I'm going to show you what it means in a moment, why we care about that one. We can find, with our cross product, we can find all kinds of stuff. We can find, we can calculate torque, we can find areas of triangles, areas of parallelograms, we can even find the volume of three-dimensional parallelograms. Later in this book, maybe in Calc 4, we will study vector fields such as gravitational and electromagnetic fields. We will also always, every time we're finding our cross product, we're finding a orthogonal vector. Then all we have to do if we want a orthogonal vector that is the unit vector is we just do our regular unit vector shenanigation, which is I'm going to divide each one of my pieces, each one of my terms, by the magnitude of that vector. So I want to find a vector that is orthogonal to u and v, given that I have this w. They're telling me that t is a real number. So I treat it as a real number, and this is going to be a heads up for we're going to get to parameterizations. It's coming. I know you're excited about it. So I, j, k, negative 1, 0, e to the t, 1, e to the negative t, and then 0. It'll be I, then the determinant, so this determinant is going to be 0, e to the t, e to the negative t, and 0, plus, oh, excuse me, that's a minus because it's that middle one, so minus k, the determinant of the negative 1, e to the t, 1 and 0, and then plus my k, and then the determinant of this smaller one, negative 1, 0, 1, and e to the negative t. When I get done, I'm going to get this vector. It's going to be negative I plus e to the t j minus e to the t k. Now, all I have to do then is take this vector and do the cross product to either this first one or this second one to show that it will be orthogonal. It's guaranteed to be orthogonal, but you could then confirm it by multiplying the dot product of u times, we'll call this w. We know that u dotted with w has to equal 0, and v dotted with w also has to equal 0. So when we're looking at our cross product, we can also find the angle between the two vectors. So we find the magnitude of my cross product, and it's going to be equal to the magnitude of my individual vectors multiplied together. These are scalars. This will be a scalar, and then multiplied by the sine of theta. This has to hold true. This gives us the theta is equal to the sine inverse of the magnitude of the cross product divided by each magnitude, and that should be v there. So u, and the magnitude of u and the magnitude of v. And why do we care? Well, we can use this to determine whether or not I have coplanar or parallel vectors. So I can determine whether or not all the vectors are on the same plane. I can also determine if two vectors are parallel. The way I do this is with the cross product. If my cross product is equal to 0, so that's saying that this part is equal to 0, I'm really doing this theta is equal to the sine inverse of 0. And that only happens when theta equals 0. That means they must be either parallel, if I have two vectors, or they're all on the same plane if I have three vectors. So if I'm trying to determine whether or not they're parallel or orthogonal or neither, the orthogonal, I use the dot product. But if I want to know if they're parallel, I use the cross product. And since we just learned the cross product, let's go ahead and do the cross product. I, j, k, 1, -4, -3, 2, -8, and -6. The determinant of this is equal to I multiplied by the determinant. I want to just stop writing the determinant, and I need to. The determinant of -4, -3, -8, -6 minus j, and I have 1, -3, 2, and -6, and then plus k, and my determinant is 1, -4, 2, and -8. And when I do this, I get 0. Because I get 0, this tells me these two vectors, even though they don't look like it, are parallel. So we talked a little bit already about the triple scalar product, and that allows us to determine, because that was up above when it was one of the definitions, my triple scalar product allows me to determine whether or not they're coplanar or not. Now the difference between just determining if two vectors are running parallel or orthogonal or neither, I would use the dot product or the cross product. Now the dot product may not tell me, in fact it doesn't tell me, whether or not these are parallel. They'll tell me whether or not they're orthogonal, but they're not going to tell me if they're parallel. So I actually have to do the cross product to determine whether or not they're parallel. I want to know if all of these are parallel. I don't care what the angle is between them. I want to know if they're all on the same plane or not. And the way I do that is I use the triple scalar product. So 3, -2, 0, 2, 3, -1, -6, -9, and 3. And notice for this, because I have this, which will produce a vector, multiplied by, or with a dot product of another vector, my answer will be a scalar. So this allows me, this triple scalar product allows me to get right to the scalar by writing it this way. Notice I don't have this top row of I, j, and k. The algorithm that we use is still the same. This time it's going to be 3 times the determinant instead of I of 3, -1, 9, and 3. And it's going to be minus a minus 2 because it's always plus, minus, plus, minus. It's by the definition. And then it's going to be the determinant of 2, -1, -6, and 3. And lastly, 0, we love 0, times the determinant of 2, 3, -6, and -9. Again, we love the 0 because that means that part is 0. Now, after doing the calculations, we end up with 0. If we end up with 0 when we are doing the triple scalar product, this tells me these are coplanar. That means they're all on they're all on the same plane. That leads into the area of a parallelogram and finding the area of a triangle. We know from pre-calculus 2 that we can find the height of a triangle if we know one of the sides and the angle not opposite that side. If we think about the height of a parallelogram now as being this magnitude times my height being the magnitude of v, the sine of theta, and it will have a base of the magnitude of u. Now these are magnitudes. These are important. It's not just u and v. These are the magnitudes. These are the lengths. Then we end up with the fact that an area of the parallelogram is the base times the height. So this is going to be the magnitude of u multiplied by the magnitude of v multiplied by the sine of theta, but this is how we define the cross product. So if I want to find the area of a parallelogram and they give me two vectors that are adjacent sides, all I have to do is find the magnitude of my cross product. So for this example, they want us to find the area of the parallelogram with its two adjacent sides and then find a triangle if they have the same two adjacent sides. So I'm going to do the cross product. I start out with I, j, and k. 3, 2, and 0. 0, 2, and 1. Finding the determinant of this. It'll be the determinant This time I got Johnny on writing the determinant. I forgot the I. So it'll be I times the determinant of 2, 0, 2, 1 minus j multiplied by the determinant. See, there it was. I forgot the determinant. The determinant of my smaller matrix when I'm doing the cofactor expansion, which is 3, 0, 0, 1, and then plus k, and the determinant, I remember at that time, of 3, 2, 0, and 2. Now, when I do this, what I get for this particular vector is I'm going to get this equal to 2i minus 3j plus 6k. Now that's the cross product. This is u crossed with v. What I now have to do is find the magnitude of u crossed with v. When I find the magnitude of u crossed with v, I'm going to get the square root of 4 plus 9 plus 36. And so I get the square root of 49, which is 7. So the area of this particular parallelogram with those adjacent sides is 7 units squared. If those two vectors are adjacent sides in a triangle, I do the same thing, but I divide by 2 when I get done, because you only want half of the parallelogram that's formed by those two sides. We can also find the volume. So the volume, a really nice, easy proof to go through in the book, can be found by the 3 adjacent sides. U with a cross product, U with a dot product of the cross product V and W. And it doesn't really matter the order. Use the order that is the easiest, and then you do the magnitude of it. Let's do an example. So I'm going to do my determinant of 1, 2, and 3, 0, 2, and 5, 8, 9, and 2, which is going to be 1 times the determinant of 2, 5, 9, and 2, minus 2 times the determinant of my smaller submatrix, which is 0, 5, 8, and 2, and then plus 3 times the determinant of 0, 2, 8, and 9. Now when I get done, I end up with a negative 9. But it's like, what? How can you have one that's negative? The magnitude of this is the same thing as the absolute value. So I found the triple scalar product. Now I have to take the absolute value. So the volume is the absolute value, which is negative 9 absolute value, which is 9, and it's my units cubed. So that's kind of cool. Get some cool stuff out of it. Okay, let's take a look at our last piece of applications at this moment in time. We'll address this later in this calculus, and then again in Calc 4, let's look at the torque. So this is tau. Measures the force that is produced by a rotation around an axis of rotation. R is the vector with an initial point located on the axis of rotation with a terminal point located at the point where the force is applied. And let F represent the force. And the torque is equal to the cross product of R and the force. What? So let's take a look at what this means. Okay. So here is my R, and here is my force. The absolute value, or the magnitude of the torque, is equal to the cross product of R crossed with F magnitude, which is the magnitude of R and the magnitude of F multiplied by the sine of theta. Let's go through a couple of examples. So we have this young person bicycling and applies a downward force of 20 pounds. So first of all, they're telling me this is the force, and also the units tell me this is a force. So I know right away my force is 20 pounds. So that's nice to know. Then they tell us that we have this angle that is 40 degrees off of the horizon. Now, what I need is not the 40 degrees, is I actually need this angle. That angle is what I need, and that angle is going to be the 90 minus 40, because we're assuming we're going to do a right triangle there. So that is my theta that I need. Now the other thing I need to pay attention to is my units. They want the answer in foot-pounds, and this is inches. So my R that I have, 6 inches, is half a foot. And this is my R. You want to kind of think of this as your radius. And in fact, this is the magnitude of your radius. It's the length of your radius. Okay, so I think I've got everything I need now, and I can just now go right to the formula. The formula is the magnitude of R times the magnitude of F multiplied by the sine of the angle. So I have my R, that's a half a foot. I have my magnitude, that's the 20 pounds. And then I just have to do the sine of 30 degrees. I multiply all this together and I get my torque. And I'm not very good at doing tau, so bear with me. And I put this in my calculator and I get 7.6604 foot-pounds. So that's my answer. Now, let's take a look at this one. We find the magnitude of the force that needs to be applied to the end of a 20-centimeter wrench located in the positive direction of the x-axis if the force applied in the direction of 0, 1, negative 2, and it produces the torque. So they're giving me the torque this time. Here's my torque. That's my tau. It's 100 Newton meters. They also tell me the magnitude of R, that's the length of my wrench, which is 20 centimeters. Now my tau is in Newton meters, so I've got to convert this into meters. So it's 0.2 meters. Now eye on the prize. We have the magnitude of the torque is equal to the magnitude of the R multiplied by the magnitude of F multiplied by the sine of theta. We have this. What we need is the sine of theta so that we can find this. So I've got to find sine theta, and the way I have to do that is I have to find the cosine, because if I find the cosine, I'll find the sine, and I know I can find the cosine because it's the dot product information. So this is the magnitude of my wrench. This is the magnitude of my wrench. The direction of my wrench is the positive y-axis. So that tells me that my wrench is going to be equal to the magnitude multiplied by the unit vector in the y-axis, which is 0, 1, and 0. So my wrench vector would be described as 0, 0.2, and 0. Now remember, I need the sine of theta. I can't go to the sine of theta without finding the cosine of theta first. I have to find the cosine of theta because I don't have enough information to go to the sine of theta. So I'm going to find the cosine. Now, if you remember, the cosine is going to be the dot product of R dotted with, I'm going to call this W, divided by the magnitude of R, which we know, the magnitude of W, and then this will equal the cosine of theta. So I need to find the dot product of R and W. My R is 0, 0.2, and 0. My W is 0, 1, and negative 2. And its dot product is going to be 0.2. I have to find the magnitude of each one of these. So the magnitude of R, which we know, is 0.2. The magnitude of W is going to be the square root of 1 plus 4, which is the square root of 5. So I have r dot w, which is 0.2, divided by the magnitude of r, which is 0.2, divided by the magnitude of w, which is 5. And this is going to equal the cosine of theta. So 1 over the square root of 5 is equal to the cosine of theta. Now, I don't really need to know theta. If I remember, the way that we define cosine is my x value over my r value. If I think of this back in trig, this is my x value over my r value, then x squared plus y squared is equal to r squared all day long. That means y must be equal to the square root of r squared minus x squared, which gives me y is equal to, let me see, the square root of 5 minus 1, which is the square root of 4, so it's just 2. So the sine of my angle is my y value, which is 2, divided by r value, which is 5. Now I could totally also do this by doing the cosine inverse. Like right here, I could have said, okay, well, I have the cosine inverse of 1 over the square root of 5, and that's going to give me some value in radians, and then I'm going to say, okay, well, I have, because it's a right triangle, then we do pi minus whatever that radian was from up above is going to give me my cosine, or my my angle for sine, and then I would just find the sine of that angle, which is way more work, I think, than just saying, oh, well, XYR is my friend all day long. And the other reason is eye on the prize. I know this, and now I know that ratio. So, putting all of the pieces together, my tau is 100. It is going to be equal to my magnitude of r, which is 0.2, multiplied by my magnitude of f, multiplied by the ratio, because the sine of theta is a ratio, of 2 divided by the square root of 5. So my final answer, f, is going to be equal to 559.017 newtons. And that's my final answer.